In a previous presentation, we dealt with whole numbers, binary whole numbers, whether they were just positive or positive and negative. And here we're going to extend our considerations to consider fractions, and then also look at hexadecimal numbers and a few other stray topics near the end. When we were on the whole number side of things, we talked in decimal about powers of 10, the ones place, the tens place, the hundredths place. And when we deal with fractions in decimal, we talk about the negative powers of 10, the tenths place, the hundredths place, the thousandths place, and so on. And it will be the same thing in binary. So in binary, when we were on the whole number side, we were talking about positive powers of 2, the ones place, the twos place, the fours place. And when we are on the fractional side, we're talking about sort of negative powers of 2, the halves place, the quarters place, the eighths place, the sixteenths place, and so on. So the dot makes up this dividing point between the sort of the whole number part and the fractional part. So on the left of the dot, we have the positive and increasing powers of 2, the ones place, the twos place. On the right of the dot, we have the negative powers of 2, and they are becoming, I don't know, increasingly negative, if you will. So the halves place, the quarters place, the eighths place, the sixteenths place, sort of 2 to a negative power, and that power is getting more negative. So we saw previously the algorithm for converting the whole number part. We take the 98 and divide it by 2, giving us a 49 with a remainder of 0, and that 0 we put into the ones place. Then we take the 49 and divide it by 2 to get 24 with a remainder of 1, and that 1 goes in the next spot, which is the twos place, and so on. So we were working in 98.61. We have that the dot is between the 98 and the 61, and we're working on the 98, and we work from the dot out, or the dot and to the left in this process of division and filling in with the remainders. Now to work with the fractional part, to work from the 0.61 from the dot to the right, instead of our previous algorithm was to divide by 2, here we will repeatedly multiply it by 2. So we'll take the 0.61 and we will multiply it by 2, and we will get 1.22. So that number before, in our result, that first number is either going to be a 1 or a 0, in this case 1.22. We take that 1, and that is in the first spot, and that is our halves place. Then we take the rest, the 0.22, and we multiply that by 2 to get us 0.44. We're going to take that 0 and we're going to put it in the next spot, and that is the quarters place. Take the 0.44, multiply it by 2, get 0.88. Take that 0, put it in the next available spot, which is the eighths place. Take the 0.88, multiply it by 2, get 1.76. Take that 1 and put it in the next available slot. So again, we're working from the dot out, but this time we're working from the dot to the right, and we are multiplying by 2's, whereas before we were dividing by 2's. So we can put the pieces together, our whole number representation and our fractional representation and the dot, and just put all the pieces together. Now I'm often asked, like, how do I know when to stop on like the 0.61? When do I stop multiplying by 2? Okay. First of all, you think you know when to stop on the 98, but as we've seen in the previous presentation, when you really stop is when you are out of bits. You say I'm going to use 8 bits to represent the whole number, or I'm going to use 16 bits to represent the whole number, and it's when you're done with the bits, that's when you really stop. And the same is true for the fraction side. You stop when you have all the bits so you choose a number of bits you're going to use to represent the fractional part, and you stop when you are out of bits. It's not, there are some fractions that sort of terminate on their own, nice fractions like a half or 3/4, but most fractions will not sort of on their own terminate. And you know this in decimals, like a fraction like a third goes on 0.33333 forever, and at just some point you stop because you're tired, or and the same thing is true here. There are many fractions can't be represented exactly in binary, and so you just decide to stop at some point. We have a finite representation. We will stop when we're out of bits. So here's just another example, 123.456. Take 123 and divide by 2, get 61, remainder of 1, and so on. So the whole number side, the integer part, we are repeatedly dividing by 2, and we are working from the decimal point to the left, where we are working away from the decimal point, and for the whole number we're working to the left. So with this second example, we're going to also show you how to check it. Or if you want to think about it another way, we're going to show you how to get the answer using the calculator. So you can use this to check your answer, or you can use this to get your answer. So find the computer's built-in calculator. Just find the list of programs. The calculator will be under C. Use that little hamburger button at the top to get the drop-down menu and choose the programmer mode, the programmer view. Make sure you're in decimal mode, which you probably will be if you just opened up the calculator, and enter the number, in this case 123, and then click on the binary to convert the number to binary. You have to do this if you want to copy and paste the number. If you just want to see the number, then you could see then it was already there when you typed in the decimal mode, and you don't have to change the mode. We obtain the fractional part by taking, in this case, the 0.456 and repeatedly multiplying by 2. So we take the 0.456, we multiply it by 2. We get 0.912. You take the whole number part of that, the 0, and that is the first position. And then you take that 0.912 and multiply it by 2 to get 1.824. And you take the whole number part, the 1, and that is the next digit, the quarters place, and so on. Again, we're going to show a check and then show how that check can then be turned into a way to get the answer in the first place. So we're going to take the number that we found for the fractional part, the 011010101. Note that the leading 0 does not appear when in the display. It was entered, but you won't see it here in the display. If we convert that binary result to decimal, we end up with 58. We want now to switch to a different view, and we're going to lose our data when switching. So before switching, let's copy that data. So we had a 58, and we need to copy it. So we can highlight the 58, right-click and choose copy, or alternatively, we can highlight the 58 and hit Control-C. We're going to switch over to scientific view, that little hamburger icon at the top, and switch to the scientific view. And then when in scientific view, highlight the number, which was a 0 because we've lost the information, and then Control-V to paste it in. After you've entered the number in scientific mode, then divide by 2 raised to the number of bits you used. In this case, we kept it to 7 bits. So divide by 2 raised to the 7th. Finally, hit the equal sign and look for the result. It's not going to be exact. Remember, we were looking for 0.456 and we got 0.453125. But again, it did not terminate at 7 bits. We just stopped, so we can't expect the answer to be exact. It's an approximation. So we can turn our check process around and turn it into a way to find the answer in the first place. So the end of the checking was to divide by 2 raised to the 7th. And so in turning the process around, we take our original fraction, 0.456, and we multiply it by 2 to the 7th, giving us 58.368. That 58 should feel familiar. We've seen that 58 before. We take that 58 and then we can convert it to binary. And we just have to remember here that we were expecting 7 bits. That's why we multiplied by 2 to the 7th. We were expecting 7 bits. And the answer we got when converting 58 only showed us 6 bits. But this tells us that we need a leading 0. In a fraction, the leading bit is the halves place, and our number 0.456 is less than a half, so we are expecting a 0 in the halves place. We are expecting a leading 0 in the fractional part. Just one more additional reminder. The algorithm we were using for the fractional parts used repeated multiplying by 2. So we're really just sort of collapsing that process. Instead of multiplying by 2 7 times, we're multiplying by 2 to the 7th, just sort of doing it all in one step. As when we played with signed and unsigned numbers, it's useful to know the sort of range of possibilities. So what we're doing right now is a fixed point, what's called a fixed point number. So you take so many bits to represent the whole number and so many numbers to represent the fraction. And so let's just say, as for a simple case, 4 bits for the whole number and 4 bits for the fraction. Then the largest number will be 1111.1111, which is 15.9375. And then the smallest number would, of course, in this case, so we're not dealing with any negative numbers here, the smallest number would be 0, but the smallest non-zero number would be 0.0001, and that's 0.0625. So that gives us the sort of range of the smallest non-zero number to the largest number. What we just did was a fixed point representation. There was a fixed number of bits for the whole number, a fixed number of bits for the fraction. An alternative to that is what's known as floating point representation. It allows us to change, to use more numbers for the whole number if we need them, or more numbers for the fraction if we need them. It's like scientific notation, and we're not going to do that now. We're going to do that later in the semester. One of the issues with binary numbers is even for a moderate-sized decimal number, it takes such a long string of bits to represent the number. But if we want to work with decimals and have our computers work in binary, then we have the problem of converting. This brings up another possible base that we could use, base 16, what are known as hexadecimal numbers. The conversion from binary to hexadecimal is far easier than it is for decimal to binary numbers. And the hexadecimal representations of numbers are much smaller and sort of easier for humans to comprehend than these sort of long binary strings. What we like about hexadecimal numbers is that it's easy to convert from binary to hex and back and forth. And this is because a hexadecimal number corresponds to 4 bits. And so with 4 bits, there are 16 possibilities, which we can think of as the numbers from 0 to 15. So the numbers go from 0000 to 1111, 16 possibilities, or the numbers 0 to 15. And then we can also have them correspond to hexadecimal digits. We will use for 0 through 9 the same digits that we use in decimal, but then when we run out of decimal digits, we will introduce the new digits in hexadecimal, and so we need 6 of them, and so we will use the letters A, B, C, D, E, F. So if we have a binary number and we want to convert it to hex, the first thing we do is we break our binary string into groups of 4 bits, also known as a nibble, and then we can just convert each nibble separately. So 1001 is 9, 1100 was a C, 1110 was an E. And so in addition to the calculator supporting decimal mode and binary mode, it also supports hexadecimal mode. Even though the computer works in binary, it will usually hide the binary from us in an attempt to be friendly. But we will sometimes see things in hexadecimal, especially addresses. An address is used to distinguish 2 things. So any things that you want distinguished, you can assign them an address and then distinguish them. So you can have computers on a network and you will give each computer its own address. Or you can distinguish hardware or input devices. So a keyboard and a mouse will each have an address. Files will have an address. Statements in a program can have an address. Characters with an individual string can have an address. When we are using addresses to distinguish things, a question that will come up is how many things can we distinguish? And that depends on how long the address is. So in the extreme example, one bit can be in two states, a high and a low, a 0 and a 1, and thus it can distinguish two things. 2 bits can be in 4 states, and thus distinguish 4 things. 3 bits can be in 8 states, and thus distinguish 8 things. And in general, n bits can be in 2 to the n states. One example of this is an IP version 4 address. An IP version 4 address is used to identify a computer network and then a computer or a host within that network. It uses 32 bits. And so we can ask the basic question, how many addresses can there be? Our answer would be 2 to the 32. And then that's the sort of highest possible number. And then there'll be rules within the system that certain addresses might not be allowed. But the upper bound, or the biggest possible number, would be 2 to the 32. We've been doing sort of numbers, but we can also use our bits to sort of represent other things, say characters. And so one standard approach for representing characters is known as ASCII, American Standard Code for Information Interchange, and it uses 8 bits to represent a character. So then that makes there 2 to the 8th possible characters, or 256. And the bottom half, the 128 of these, are fairly standard, and then the sort of upper half of ASCII is sometimes variable. The 256 characters of ASCII is pretty limited, so it gets extended by Unicode. Unicode sort of starts with 16 bits, so how many characters can you represent then? If we're just doing our simple calculation, it would be 2 to the 16. And that's going to give us enough for English and Chinese and Arabic and so on. But actually, Unicode goes beyond this. It's extensible. So there are codes within Unicode that might announce that, oh, this time I'm going to use 32 bits or so on. But ASCII, while limited, is sort of a legacy system, and one still sees it around, so one should be familiar with, for instance, that capital A corresponds to the number 65, little a corresponds to 97, and so on.